So hello all, my name is Jonathan Arthurito Sinaga, and now I'm going to talk about video compression. What is a video? Video, whether analog or digital, is represented by a sequence of discrete images shown in quick succession. Each image in the video is called a frame, which is represented as a matrix of pixels defined by a width, height, and pixel depth. What is a compression? Why do we need it for? Doing or sending digital data with its content remaining intact is the obvious way any person will distribute his or her content throughout the internet. But executing that will be so expensive since we are gonna need a high internet bandwidth and a gigantic amount of space to handle the storage. Even though the storage industry is still growing, where we could see many vendors who sell greater memory storage with a lower price, digital contents industry seem to also do the same. Motivated by this problem, doing compression before sending any digital contents will surely reduce the size of that content, which automatically will imply slower storage requirements and faster delivery time. Compression. Compression refers to the process of reducing the size of multimedia files, such as image, audio, and video, to make them more manageable for storage, transmission, and processing. The primary goal of compression is to minimize the amount of data needed to represent the multimedia content while preserving its essential quality or its content. How to do the compression? One obviously naive way is to compress each individual image, as video itself consists of an array of images. The idea of image compression is that we use the redundancy in the image to generate a newly compressed image. We can do this based on the fact that for each individual photo or image, there is definitely some subblock or macroblock that has a same characteristic. This thing is called spatial redundancy. We can generalize it or do it in a higher dimension. In videos itself, it is intuitive to think that for each consecutive or adjacent image, there is definitely some kind of redundancy or similarity between them. As you can see in this video, in this image itself, nothing much has been changed beside the woman's hand. Moving from this to this, we can exploit this fact, namely temporal redundancy, to utilize or optimize our video. Block-based frame prediction. To harness the temporal redundancy, we are gonna use something called block-based frame prediction. In block-based frame prediction, we could predict partially the next frame by using the previous frame and the data about the factor that tells the direction and magnitude of the next subblock for each subblock. Assuming that we are in frame n and want to compress frame n+1 by making a prediction out of frame n. Divide the frame n into its corresponding macro block and associate or find the similar macro block in the frame n+1. We can represent it as a vector where the starting point is the macro block in frame n and the ending point is the macro block in frame n+1. But having a list of vectors of moving macro blocks doesn't guarantee that our predicted n+1 frame will look the same as the real frame n+1, because the possibility of existence of foreign or new pixels in the new frame. As you can see in here, there is some kind of foreign thing or pixel, where you can see a pistol in this image and not in this one. And here's the overall schematic of how the thing works. This is called as open loop encoding. First, for each adjacent frame, actually, we'll calculate the motion factor and then find the difference image. And after that, we can construct the n+1 image by encoding the compressed difference image added with the encoded motion factor. But it isn't always going to be optimal. Let us reconstruct the video with n frame as an array with size of n, indexed from 1 to n. Initially, we can compress or treat frame 1 just as normal image compression, and for each frame I from 2 to n, we can construct frame I using quantized frame I-1. I think the problem is already obvious enough. Using quantized frame I to predict frame I+1 to frame n will render all frame 1 plus 1 to frame n prone to error, since the quantized frame itself frame 1 itself or frame I itself doesn't really represent the original image. Here is why the closed loop encoding comes. Closed loop encoding has a more beneficial advantage from the open loop encoding by realizing that the product of open loop encoding is because they are doing the encoding with the original image while doing the prediction using the previously quantified or quantized image. In closed loop encoding, motion compensation or frame difference is calculated by only the difference between real frame I plus 1 and quantized frame I. This is more powerful since the process of decoding could be regarded just like a reconstruction of encoding progress or process. And now I'm going to talk about the type of prediction. There are three types of prediction: I frame, P frame, and B frame. The I frame. I have mentioned something like this before in the beginning of the presentation. We could treat a video as an array of images, and then we are going to compress the image individually. That is the idea of I-frame prediction. And for P-frame, this is the idea of the adjacently predicting predictions. A frame could be used as a reference point, like frame I in this photo, to calculate one or several consecutive frames by calculating the motion compensation factor and the image difference. As you can see here, the P frame is referring to I frame. The reference frame usually predicted by using the number one prediction of I frame, just like what I have mentioned before. This is the idea that I mostly told about for the whole video, but the reference frame doesn't have to be on one. It means that for a whole video there could be several iframe and then followed by a certain number of p-type frames like this. There is 3 iframes in this image. And then for the B-frame, the idea of B-frames is basically using already predicted P or I frames or both, be it in the front or back of the frame, and create the prediction like this. For the frame B, it will need frame I in the back of it and frame P in the front of it to predict itself. What I mean by already predicted is that the reference frame P or I or both need to be generated first before predicting of what frame B is going to be like. I think that is all from me. Thank you.